Have you ever looked at a motor nameplate and felt like you're reading a secret engineering language? Numbers everywhere: volts, amps, kilowatts, RPM, power factor, and somehow all of them matter. But here's the truth. If you can read a motor nameplate correctly, you can understand how the motor works, how to connect it, how much power it consumes, and even how long it will survive. In this video, I'll teach you how to read a three-phase motor nameplate, step by step. By the end, you'll look at any motor and instantly understand what it's telling you. Let's get started. A motor nameplate is basically the motor's identity card. It contains all the electrical and mechanical information defined by the manufacturer to ensure safe and efficient operation. Ignoring these values is one of the most common reasons for motor overheating, inefficiency, and failure. So every number here exists for a reason. First, we look at rated power. You'll usually see it written in kilowatts kW or horsepower HP. This does not mean the electrical power consumed. It means the mechanical output power delivered at the shaft under rated conditions. For example, a 7.5 kilowatts motor delivers 7.5 kilowatts of mechanical energy, not electrical input power. The electrical input is always higher because no motor is 100% efficient. Next comes one of the most important parameters, voltage. You may see something like 230/400ths V or 400/690ths V. This indicates dual voltage operation. It tells you how the windings should be connected. Lower voltage is for delta connection, and higher voltage is for star connection. Connecting the motor incorrectly can instantly damage it. So this value directly determines wiring configuration. Right beside voltage, you'll find rated current measured in amperes. This is the current the motor draws at full load under rated voltage and frequency. Engineers and electricians use this value to select cable size, choose circuit breakers, set overload protection. If the motor continuously draws more than this current, something is wrong, either mechanical overload or electrical problems. Right under voltage and current, you'll find frequency. It is measured in hertz, and it is equivalent to electrical cycle per second, usually 50 hertz or 60 hertz. Frequency affects motor speed. Higher frequency, higher RPM, lower frequency, lower RPM. Running a motor at the wrong frequency without adjusting voltage can reduce torque. To maintain performance, the V/F ratio should stay constant. Some motors are dual frequency rated and can safely run at both 50 and 60 hertz at the proper voltage. Right next to the electrical ratings, you will find the power factor, usually written as cosine phi. Power factor represents the deviation between the voltage waveform and the current waveform inside the motor. Its value ranges between 0 and 1. A value close to 1 means voltage and current are almost in phase. Electrical power is used efficiently. A lower value means more reactive power and higher current for the same useful output. In simple terms, the closer the power factor is to 1, the better the motor utilizes electrical energy. Motor nameplates typically show the power factor at full load conditions, not during startup or light load. Just below the power factor, you'll usually see efficiency, written as a percentage. Efficiency tells us how much electrical input power becomes useful mechanical output power. For example, an efficiency of 90% means 90% converted into mechanical motion. 10% lost as heat, friction, and magnetic losses. Modern motors may also include efficiency classes such as IE1, IE2, IE3, or IE4. Each class corresponds to standardized efficiency levels, and you can easily find official efficiency classification tables online to see how these categories compare. Moving toward thermal limits, you'll find the insulation class, typically marked as a letter like B, F, or H. This value defines the maximum temperature the winding insulation can safely withstand without degradation. Higher insulation class means higher thermal tolerance and longer motor life under demanding conditions. However, insulation classes are not arbitrary letters. They come from standardized temperature rating tables. Searching for an insulation class temperature chart will show you the allowable temperature limits and temperature rise associated with each class. Understanding these tables helps explain why two motors with the same power rating may survive very different environments. Close to the mechanical specifications, you'll find the IP rating, short for ingress protection. An example might be IP55. This rating consists of 2 digits. The first digit indicates protection against solid objects and dust. The second digit indicates protection against water. Higher numbers mean better protection. IP ratings follow an international standard classification, and there is a well-known IP protection table that explains exactly what every number means. It's highly recommended to look up this table. It immediately tells you whether a motor is suitable for outdoor, dusty, or wet environments. Another important parameter is the duty cycle, identified by symbols like S1, S2, or S3. Duty cycle describes how the motor is intended to operate over time. For example, S1, continuous operation, S2, short time duty, S3, intermittent periodic operation. Each duty type defines heating and cooling behavior of the motor. These classifications are standardized, and you can find duty cycle reference charts that explain operating patterns visually. Many motor failures happen simply because a motor designed for intermittent duty is forced to run continuously. Now, one parameter many people overlook is the kVA code, sometimes called the locked rotor kVA code. This letter code indicates the starting current characteristics of the motor. During startup, an induction motor can draw several times its rated current, and the kVA code helps engineers estimate that inrush current without complex calculations. Each letter corresponds to a specific range of kVA per horsepower during locked rotor conditions. Manufacturers follow standardized kVA code tables. Searching for a NEMA kVA code chart will show how each letter relates to starting current levels. This information is extremely useful when selecting circuit breakers, contactors, and protection devices. Near the bottom of many nameplates, you may find bearing information such as numbers like 6,205 or 6,306. These numbers specify the exact bearing type used inside the motor. They allow maintenance teams to replace bearings correctly without disassembling or measuring components. Bearing numbering systems also follow international standards, and reference tables are available online, explaining dimensions and load ratings for each bearing code. You may also notice abbreviations such as DE and NDE in the bearing section of the motor nameplate. DE stands for drive end. This refers to the bearing located on the side of the motor where the shaft connects to the mechanical load. NDE stands for non-drive end. This is the bearing located on the opposite side of the motor, the rear side that is not directly connected to the driven equipment. You may also notice something called the frame size on the motor nameplate. Frame size refers to the standardized physical dimensions of the motor, including shaft height and mounting dimensions. Numbers like 90, 112, or 132 correspond to international standards such as IEC or NEMA. This standardization ensures that if a motor needs replacement, another motor with the same frame size will fit the same mounting position without mechanical modification. You can easily find frame size reference tables online that show the exact dimensions for each frame number. Besides the electrical and mechanical specifications, you may also find some additional information on the motor nameplate. For example, the manufacturer's name, the motor model number, and the serial number. The manufacturer's name tells you who produced the motor, while the model number identifies the exact motor design and configuration. The serial number, on the other hand, is unique for each individual motor. It allows manufacturers and maintenance teams to trace production details, manufacturing date, and service history. These details may seem less technical, but they are extremely useful when ordering spare parts, requesting technical support, or replacing the motor with an identical model. And that's how you can read a 3-phase motor nameplate in a very simple way. If you found this video helpful, don't forget to like the video and subscribe for more engineering or scientific content. Thanks for watching.